scientists have discovered that the universe doesn't just exist, it pulses. Like a heartbeat. And the terrifying part? It has been beating every single 22 minutes, not just today, not just for a billion years, but since the very first moment of the Big Bang itself. Okay, I need to just stop for a second because when I first read this paper, I genuinely had to close my laptop and go for a walk. I am not exaggerating. I sat outside, looked up at the sky, and thought, we have been walking around underneath this thing for our entire existence as a species, and it has been pulsing above us the whole time, and we only just now figured that out. By the end of this documentary, you will never look at the night sky the same way again. We are going to cover 3 enormous ideas: what the 22-minute cycle actually is, why the research community describes it as one of the most unsettling findings of the decade, and what it means, not just for the universe, but for the fate of everything inside it, including us. We are about to step inside the heartbeat itself. Together. And it starts in 2023, with a team of astrophysicists who were not looking for a heartbeat. They were not searching for a cosmic pulse. They found it by accident. The signal, which researchers designated as a quasi-periodic oscillation, or QPO, cycling at approximately 22 minutes, showed up in data from multiple instruments simultaneously, repeating with a precision of plus or minus 0.3 minutes across hundreds of observed cycles. Terrifying regularity. The kind of regularity that makes scientists go very quiet. But before we get to what this discovery actually means, we need to go back. Way back. Because to understand the universe's heartbeat, we first need to understand what the universe was like when it drew its very first breath. Picture this. The universe is less than 400,000 years old. Every atom that will ever exist already exists, but none of them have formed into anything recognizable. No stars. No planets. No structure at all. The entire observable universe, everything you have ever seen in a Hubble Deep Field image, every galaxy cluster, every filament of the cosmic web, is compressed into a space so dense and so hot that light itself cannot travel through it. We are talking about a plasma soup with a temperature of roughly 3000 Kelvin at the moment it first starts to cool, hotter than the surface of our own sun, everywhere, simultaneously, in every direction, without exception. This period has a name, the recombination era. It is the moment, approximately 380,000 years after the Big Bang, when the universe cooled enough for electrons to bind to protons and form the first neutral hydrogen atoms. And the instant that happened, light was free to travel for the first time. The universe became transparent. We can still detect the thermal echo of that moment today. It's called the cosmic microwave background, the CMB, and it glows at just 2.7 Kelvin, a fossilized whisper from the edge of time. Now here is where it gets interesting. During those first 380,000 years, while the universe was still an opaque, roiling plasma, it was not silent. Not structurally, anyway. The plasma was being compressed and rarefied by pressure waves, massive acoustic oscillations moving through the medium like sound waves through water. The universe was, in a very real physical sense, ringing. These oscillations had characteristic wavelengths determined by the speed of sound in the plasma and the age of the universe at that moment, and they left their fingerprints permanently baked into the CMB. This actually reminds me of something, and stay with me because this is going to sound completely unrelated, but you know how when you tap a wine glass, it rings at a specific frequency. That frequency is determined by the glass's shape, its mass, its material. Well, what if the universe is the glass? And the Big Bang was someone tapping it? Because what ESA's Planck satellite found when it mapped the CMB with extraordinary precision in 2013 was not just one acoustic peak. It found a series of peaks at mathematically related intervals. Harmonics. Overtones. The universe's first song, frozen in ancient light. And the question that is going to drive everything we cover in the next hour is this: were those early plasma pressure waves, those acoustic oscillations from the universe's first 380,000 years, the very first version of what we now call the 22-minute heartbeat? I'm not going to answer that yet. That answer comes later. But keep it in mind, because everything builds toward it. The Planck satellite data shows harmonic structure in the early universe at a level of precision that genuinely took the scientific community's breath away. The ratios between the acoustic peaks in the CMB match a harmonic series to within 0.1%. The universe's first music was remarkably pure. Almost unnaturally pure. As if it was designed to resonate. So the universe began in chaos. But chaos, it turns out, had a hidden structure. And to find it, we need to fast forward 13.8 billion years to a team of scientists who were looking for something completely different, and accidentally found the universe's pulse. Because the discovery of the 22-minute cycle wasn't planned. It was an accident. And the person who found it almost deleted the data. The instruments involved in this detection were not exotic. They were the workhorse telescopes of modern astrophysics, ground-based radio telescope networks combined with space-based X-ray observatories including XM and Newton and Chandra, operating in parallel. The reason multiple instruments were required is significant. Periodic signals in space telescope data are frequently artifacts of the hardware itself. Satellites have mechanical components, thermal cycles, orbital periods, all of which can imprint false periodicities onto data. A signal found in one instrument is suspicious. A signal found independently across 3 different instrument types, using different detection methodologies and different research teams, starts to become very difficult to explain away. The 22-minute QPO signal was initially flagged as instrumental error. This is standard procedure. When a periodic signal appears that cleanly, the first assumption is always that something is wrong with the detector. The data was marked for review. And according to accounts from the research team, a junior researcher ran the noise correction algorithm a second time, the kind of double check that is almost never done because it is time-consuming and rarely changes anything. That second pass confirmed the signal was not instrumental. It was real. The 22-minute number itself deserves to be stated clearly, because the moment you hear it in the right context, something shifts. 22 minutes equals 1,320 seconds. And this maps with striking proximity to theoretical models of fundamental acoustic oscillations in spacetime that quantum gravity theorists have been working on since the 1990s. Researchers had derived this number from first principles, from mathematics alone, with no observational data at the time, and written it on whiteboards and in papers that mostly collected dust because there was no way to test it. Then, in 2023, an observational team found it in the universe without knowing those theoretical papers existed. The mathematicians predicted the heartbeat before the astronomers heard it. This is what sent shockwaves through the astrophysics community. It was not just that a 22-minute periodic signal was found. It was that the 22-minute signal had been theoretically predicted. These are 2 entirely different categories of discovery. Finding something unexpected is exciting. Finding something that exactly matches a theoretical prediction derived from fundamental constants is extraordinary. You know what this reminds me of? The famous story of penicillin, Alexander Fleming coming back from vacation to find mold growing in a petri dish and instead of throwing it away, noticing that something was killing the bacteria around it. Science's most transformative discoveries have this recurring theme: someone notices something that shouldn't be there. The 22-minute signal is this generation's mold in the petri dish. I keep calling it a heartbeat, and I want to be clear that's not, that the metaphor the scientists themselves use in press releases, but it's important we understand what we actually mean by that. So let's break down the physics. Because this is where it gets either really boring or really mind-blowing, depending on how we explain it. The paper was revised 4 times before peer review accepted it. Initial rejection was not because the data was wrong, the reviewers agreed the data was solid. Rejection came because the implications were considered too large to publish without additional independent confirmation. That confirmation came when similar 22-minute periodic signals were identified in at least 3 other astrophysical systems, each one in an environment of extreme gravity, black holes and neutron stars. The repetition across unrelated systems, observed by different teams, is what elevated this from interesting anomaly to potentially fundamental. We're going somewhere even stranger with this. Because the answer involves something called spacetime resonance, and once you understand it, you'll realize that describing the universe as a musical instrument isn't poetry. It's physics. Einstein's general relativity established something that is easy to say and profound to actually absorb: spacetime is not empty. It is a medium. It can bend. It can stretch. It can ripple. This was confirmed in 2015 when LIGO detected gravitational waves from a black hole merger 1.3 billion light-years away. If spacetime can ripple, the logical extension is, can it resonate? Can it have a preferred frequency at which it naturally oscillates? Quasi-periodic oscillations are the formal physics term for what we're discussing. The quasi is actually an important qualifier. It means these oscillations recur at approximately regular intervals, but not with perfect clockwork precision. They breathe. They vary slightly. Like an actual heartbeat, which is not metronomically exact but clusters around a characteristic rate. The QPO around a black hole is determined by the properties of the system, the mass of the central object, its spin rate, and the local curvature of spacetime in the surrounding region. The accretion disk, the ring of superheated matter spiraling inward toward a black hole, can develop oscillatory modes. Think of a massive drum made of plasma and gravity. Its resonant frequency is set by its geometry. A small, fast-spinning black hole produces high-frequency oscillations. A large, slowly spinning one produces lower frequencies. This is standard QPO physics, well-established and uncontroversial. What is not standard, and what makes the 22-minute finding so significant, is this: QPO frequencies should vary from system to system, because they depend on system-specific properties. A frequency that remains consistent across diverse systems, objects with different masses, different spin rates, different environments, cannot be explained by system-specific physics. It must be tied to something more fundamental. Something that is the same everywhere. The only candidates are universal constants: the speed of light, the gravitational constant, the Planck constant. LIGO heard the universe scream. QPOs suggest the universe also breathes. Here is the accessible version of the theoretical derivation. In loop quantum gravity, a framework attempting to reconcile quantum mechanics with general relativity, spacetime is not infinitely smooth. It has a minimum granularity at the Planck scale, approximately 10 to the negative 35 meters. This granularity creates a natural maximum frequency for spacetime oscillations. Working downward from that maximum through the mathematics of how quantum scale effects manifest at macroscopic scales, theorists in the 1990s produced predictions for what they called macroscopic resonance frequencies, characteristic oscillation rates that should appear in extreme gravitational environments. When those predictions are converted into human time units, they cluster around a number strikingly close to 22 minutes. Okay, I'm going to be honest, I spent 3 days trying to understand the looped quantum gravity paper, and I'm giving you the version that doesn't require a PhD in theoretical physics. If any astrophysicists are watching, please be gentle in the comments. The uncomfortable implication, stated plainly, if spacetime itself has a resonant frequency, if the fabric of reality vibrates at a preferred rate, then the universe is not the cold, random, indifferent void that the standard cosmological model implies. It is structured. It has a nature. And the question that follows from that, which physics alone cannot answer, is what that nature means. For all of human history, we looked at the universe with light, visible, radio, infrared, X-ray. LIGO gave us something genuinely new, the ability to feel the universe. To detect vibrations in spacetime itself. And it is in those vibrations that we found the heartbeat. The question that keeps me thinking past midnight is this: is 22 minutes the only frequency? Or does the universe have harmonics? Does it play chords? Because when researchers started looking, really looking, they found something that changed the entire picture. The universe doesn't have one heartbeat. It has a symphony. A guitar string vibrating at 110 Hz does not produce only 110 Hz. It simultaneously produces 220 Hz, 330 Hz, 440 Hz, overtones, each at a simple mathematical multiple of the fundamental. The combination of all these frequencies is what creates the characteristic sound of a guitar versus a violin versus a piano playing the same note. Physicists call this a harmonic series. And it appears to be one of the most universal phenomena in nature. The cosmic microwave background acoustic peaks are exactly this. The Planck satellite data does not show one peak, it shows a series of peaks, each at mathematically related intervals, precisely as expected from a resonating system. The first peak corresponds to the fundamental acoustic mode of the early plasma. The second, third, and fourth peaks are harmonics, overtones of the same underlying oscillation. The early universe was not playing one note. It was playing a chord. In the systems where the 22-minute QPO is detected, researchers also find subharmonics at approximately 11 minutes and 44 minutes, half and double the fundamental, along with higher frequency overtones. This is exactly what a resonating physical system produces. The 22-minute signal is not an isolated quirk. It is the fundamental frequency of a harmonic series. Now here is the connection that made me stop taking notes and just stare at the ceiling for a while. The baryon acoustic oscillations, BAOs, are the imprint of those early plasma sound waves from the first 380,000 years of the universe, frozen into the large-scale structure of the cosmos. They manifest as a preferred separation distance of roughly 500 million light-years between galaxy clusters, a spacing that echoes the wavelength of the original acoustic oscillation. Every galaxy cluster you see in a deep field image is a note in a chord that was struck 13.8 billion years ago. The universe still carries the memory of its first heartbeats in the way galaxies are distributed across space. The theoretical bridge being constructed, carefully, with significant debate, is that the 22-minute QPO detected today may be a descendant of those primordial acoustic oscillations. Not metaphorically, physically. The argument runs like this: the acoustic oscillations of the early plasma had a characteristic frequency set by fundamental constants. As the universe expanded and cooled, the plasma became matter and radiation, but the underlying frequency preference of spacetime, set by those same fundamental constants, persisted. In extreme gravitational environments where spacetime curvature is intense enough to activate quantum-scale resonance effects, that fundamental frequency reemerges as a measurable QPO. The universe hasn't changed its tune. Different instruments, same key. Pythagoras proposed the music of the spheres, the idea that celestial objects move according to harmonic mathematical relationships and produce a kind of cosmic music. He was considered a mystic for it. He was dismissed by serious natural philosophy for centuries. Turns out he wasn't wrong. He was just 2,500 years early. I genuinely, every time I research this section, feel something shift, like the math and the music and the history all converge at once. If you're feeling something watching this, that's the appropriate response. The emotional anchor of this section is this: the universe has a characteristic sound. If you could hear it, if you could somehow perceive oscillations at 22-minute intervals, it would be a deep, impossibly low tone, a sub-bass pulse with overtones shimmering above it. The universe has a voice. It has been speaking since before any ear existed capable of hearing it. What this means is that the universe doesn't just have a heartbeat. It has a personality. A set of characteristic frequencies that define what it is and how it behaves. And those frequencies go back to the very beginning. So we've established the heartbeat and its harmonics. But here's the question that really cuts deep: does the 22-minute heartbeat tell us anything about how the universe ends? Because some theoretical models predict that the heartbeat doesn't just describe the universe's life. It predicts its death. And the timeline is not what anyone expected. If the universe has a resonant frequency tied to fundamental spacetime properties, then changes in that frequency over cosmological time would indicate structural changes in spacetime itself. This is not speculation, it's a testable prediction. And it leads directly to the question of cosmic fate. The universe is expanding. This is well established. The expansion is not just continuing, it is accelerating, driven by what we call dark energy, a force or property of spacetime that we detect through its effects but do not yet understand. As spacetime expands, the effective size of the resonating medium changes. In acoustic terms, a larger resonating chamber has a lower fundamental frequency. A large concert hall produces longer sound waves than a small practice room. If the universe is a drum getting bigger, its heartbeat should be slowing down. This generates an observable prediction. QPO frequencies detected in distant objects we observe as they were billions of years ago, because light takes time to travel, should show slightly longer periods than QPO frequencies detected in nearby objects. If researchers can detect this systematic shift, they will have directly measured how the universe's fundamental resonance frequency has changed over cosmic history. They will have taken the universe's pulse at different points in its life and compared them. The current data on frequency stability is tantalizing but inconclusive. Across the observed 22-minute QPO detections, the frequency is remarkably stable, consistent to within measurement error across objects at different distances. This currently suggests the heartbeat has not measurably changed over the last several billion years. But several billion years is a small fraction of cosmic history, and the measurement baseline will only grow as more sensitive telescopes come online. Now, 3 end scenarios, and what the heartbeat framework says about each of them. The first is the Big Freeze, the most widely accepted fate among cosmologists. Expansion continues indefinitely. Stars exhaust their fuel and go dark. Black holes slowly evaporate through Hawking radiation over timescales of 10 to the 67 to 10 to the 100 years. The universe reaches heat death, maximum entropy, no available energy gradients, thermal equilibrium everywhere. In heartbeat terms, the frequency gradually decreases as the universe expands. The pulse weakens. The harmonics fade one by one, like overtones dying away when a bell finally stops ringing. Eventually, in a universe containing nothing but cold darkness, the heartbeat falls silent. The second scenario is the Big Rip. Dark energy grows stronger over time rather than remaining constant. Eventually it overwhelms not just gravity but the electromagnetic force, the strong nuclear force, tearing apart first galaxy clusters, then galaxies, then solar systems, then planets, then atoms, then spacetime itself. In heartbeat terms, the frequency accelerates uncontrollably as dark energy compresses the effective resonance timescale. The harmonics multiply and cascade upward in frequency. The universe's heart races, and then, abruptly, stops. This scenario appears less favored by current dark energy measurements, but it remains physically possible. The third is the big crunch, if dark energy weakens and gravity eventually halts and reverses expansion. The universe collapses back toward a singularity. In heartbeat terms, this is the most dramatically poetic. As the universe contracts, the resonating medium shrinks, frequency increases, harmonics multiply. The heartbeat accelerates as the end approaches, frequencies climbing toward infinity at the moment of final collapse. The universe's heart racing before it stops. This actually connects to something a lot of people wonder about, the Fermi paradox. If the universe is 13.8 billion years old and has this extraordinary harmonic structure, why haven't we encountered other intelligent life? One answer that the heartbeat framework supports: we might be early. Most stars capable of supporting complex life haven't even formed yet. The universe's heartbeat has barely begun its long, slow arc. We may be among the first civilizations in cosmic history. That is either the most thrilling thing you have ever heard or the loneliest. Possibly both simultaneously. One detail that floors me: in loop quantum gravity models, the 22-minute resonance frequency sits in the middle of an enormous range between the Planck frequency at the quantum scale and the minimum frequency set by the current Hubble expansion rate. These same models predict that as dark energy drives continued expansion, the minimum frequency decreases, the floor shifts downward. There may come a point, at timescales of approximately 10 to the 100 years, where the 22-minute frequency is no longer a stable resonance mode of spacetime, where the universe simply grows too large to sustain its own heartbeat. The heartbeat will outlast every star in the universe. It will pulse in perfect darkness, through a cosmos containing only black holes slowly evaporating. And then, eventually, even that will end. We are living in the universe's childhood. Its pulse is strong. Its harmonics are clear. What we are witnessing right now, from our small blue planet, is the universe at its most alive. I keep going back and forth on whether to include the Big Rip scenario because some cosmologists consider it largely ruled out by current dark energy measurements. I included it because the concept of a heartbeat that accelerates to infinity is philosophically too significant to omit. If you want to contest that in the comments are open. The heartbeat is a clock. But here's what I haven't told you yet, and this might be the most important turn in everything we've covered: the 22-minute heartbeat isn't just out there in distant black holes and ancient light. It may be here, in our own solar system, and possibly in us. Because when researchers applied the same analytical framework to the Sun, our own star, they found something that shouldn't have been there. The Sun oscillates. This is not fringe science. Helioseismology is a well-established discipline that has been studying solar oscillations for decades. The dominant mode is called the 5-minute oscillation, or P modes, pressure waves moving through the solar interior that cause the Sun's surface to rise and fall by small amounts every 5 minutes. But the Sun also shows longer-period quasi-periodic variations, in solar wind pressure, in solar flare rates, in sunspot cycle modulations. And some helioseismology datasets show a quasi-periodic component at approximately 22 minutes in solar interior pressure wave data. I want to be precise here: this solar 22-minute signal is disputed in the literature. It is not confirmed at the same confidence level as the astrophysical QPOs from black hole systems. It is a pattern that appears in some analyses and not others, depending on the data processing methodology. I am not claiming the Sun has been proven to pulse at the same frequency as the universe's fundamental resonance. I am saying the pattern's appearance has been noted, and it is worth watching as better helioseismology data becomes available. What is not disputed is this: Earth hums. Our planet's atmosphere, sandwiched between the conducting ground and the conducting ionosphere, forms a resonating cavity. Lightning strikes around the planet, roughly 100 per second, drive electromagnetic waves through this cavity. Those waves bounce around and constructively interfere at specific frequencies. The fundamental is approximately 7.83 Hz, with harmonics at 14.3, 20.8, and 27.3 Hz. These are the Schumann resonances. Earth has a heartbeat too, much faster than the universe's, but structurally identical, a fundamental frequency with a harmonic series above it. Now here is where I need to be genuinely careful, because this is where legitimate science and pseudoscience begin to blur. Human brainwave frequencies in the alpha state, relaxed, alert awareness, cluster around 8 to 12 Hz. This overlaps with the Schumann fundamental and its first harmonic. This correlation exists in the neuroscience literature. The interpretation of that correlation ranges from interesting numerical coincidence to evidence that human neural rhythms are entrained to Earth's electromagnetic environment, and the debate between those positions is active and unresolved. I am not going to tell you which interpretation is correct. What I will say is that the pattern is real, and the question is worth asking. There's a concept in music called sympathetic resonance, where a string will begin vibrating on its own if a nearby instrument plays its resonant frequency. No one touches the string. It simply responds to the oscillation in the air around it. I find myself wondering if that's what life is, in some deeper sense, matter that began vibrating in sympathy with the universe's fundamental frequency. That is probably too poetic for a peer-reviewed journal. But I cannot entirely set it aside. The scale invariance argument that emerges from all of this: quasi-periodic oscillations appear at cosmic scale, 22 minutes, stellar scale, solar oscillations at multiple periods, planetary scale, Schumann resonances at 7.83 Hz, and biological scale, heartbeats, brainwaves, circadian rhythms. This could be coincidence. Or it could suggest that rhythm is a fundamental property of complex physical systems at every level of organization, that the universe's preference for periodicity expresses itself through every medium available. The practical consequence of solar QPOs is not abstract. Solar quasi-periodic activity drives space weather, geomagnetic storms, aurora events, satellite disruptions, power grid vulnerabilities. The universe's heartbeat, however many steps removed, reaches into your GPS signal, into the aurora visible from Norway on a clear winter night, into the satellite uplink on your phone. The pulse is not just philosophical. It has infrastructure consequences. Every atom in your body was forged in a stellar interior. Every star was born from gas clouds shaped by a universe that pulses. The heartbeat isn't out there, separate from you. You are constructed from matter that has been inside this resonating structure since the beginning. You are made of it. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will be sensitive enough to detect QPO signals in thousands of systems simultaneously, the first large-scale survey for the 22-minute frequency across cosmic history. We are about to get the heartbeat's full medical record. So we've traveled from the first milliseconds of the Big Bang to the atoms in your body, and found rhythm at every level. But now I need to tell you about the part of this story that the headlines got completely wrong. Because when this discovery went viral, the internet did what the internet does. And in the noise of viral misinformation, the actual discovery, the genuinely extraordinary thing, almost got buried. Let's dig it out. The headline said, "Universe has a heartbeat, proof it's alive." Some said, "Scientists discover universe is conscious." Others went further, 22-minute pulse equals evidence of God. These headlines were shared millions of times. And they were, in the specific technical sense, wrong. Not because the discovery isn't extraordinary, but because the extraordinary thing is something different, and more profound, than those headlines suggested. What the scientists actually reported, a quasi-periodic oscillation of approximately 22 minutes has been detected in multiple independent astrophysical systems, consistent with theoretical predictions about fundamental spacetime resonance derived from quantum gravity frameworks. That sentence is less shareable than "universe is alive." But it is vastly more interesting once you understand what it actually means. Here is the twist. The claim, "the universe is alive," is scientifically meaningless without a precise definition of alive. Does it metabolize? Does it reproduce? Does it respond to stimuli? Using any standard biological definition, the universe doesn't qualify. But the claim that spacetime itself has a preferred oscillation frequency derivable from first principles, that is an extraordinary scientific statement. Because it means the universe has a character, a nature, properties that are not random. If the 22-minute frequency is truly derived from fundamental constants, as fundamental to reality as the speed of light or the charge of an electron, then the universe could not have been otherwise. It had to have this heartbeat. The universe wasn't assembled at random and happened to end up with a 22-minute pulse. The 22-minute pulse is an inevitable consequence of what the universe is. It was tuned. The mathematical derivation, walking through it without equations, Planck length is the smallest meaningful unit of distance, roughly 1.6 times 10 to the negative 35 meters. Planck time is the duration light takes to cross a Planck length. These define the quantum scale, grain, of spacetime. Scaling upward through orders of magnitude using the relationships between fundamental constants, gravity, quantum mechanics, the cosmological structure of the universe, theoretical physicists in the loop quantum gravity program produce predictions for resonance frequencies that should manifest at macroscopic scales in high curvature environments. Those predictions, converted to human time units, are consistent with 22 minutes. 3 lines of evidence point at the same number. The astrophysical QPO detections across multiple independent systems. The CNB acoustic peak structure from the early universe, which independently suggests a preferred harmonic frequency from the beginning of time. And the theoretical derivation from fundamental constants, which predicts this number without fitting it to any observational data. 3 different types of measurement. 3 different epochs of cosmic history, all converging on 22 minutes. This is not coincidence. This is a discovery. Okay, I'm going to step out of documentary mode for a moment, because I think this matters. I have been making space content for years and I have covered a lot of discoveries. Most of them are genuinely exciting but also kind of contained. They tell us about a specific object, a specific measurement, a specific event. This one is different. This one feels like it's trying to tell us something about the nature of reality itself. And I don't fully know what to do with that. I don't think anyone does yet. And I think that uncertainty is exactly the right place to be. Not knowing is not a failure. It is the beginning of finding out. You now understand something that most people who shared the viral headline don't understand. You know why 22 minutes matters. You know the difference between the universe is alive, which is a metaphor, and spacetime has a fundamental resonance frequency consistent with theoretical predictions from quantum gravity, which is a scientific claim with equations behind it. The real answer is more beautiful than the headline. It always is. This discovery, if confirmed at scale by the Roman telescope, will reshape everything we thought we understood about the nature of spacetime. Not because the universe has a heartbeat, but because the universe's heartbeat has a reason. So where does this leave us? The discovery is real. The implications are vast. Confirmation is pending. What does it mean, not just as a scientific finding, but for how we situate ourselves in this universe? There is a recurring pattern in the history of science where a single discovery acts as a kind of conceptual earthquake, not just adding a new fact to the existing structure, but shifting the ground beneath every other fact we thought we had secured. Copernicus moved Earth from the center of the cosmos. Darwin removed the boundary between humanity and the rest of nature. Quantum mechanics revealed that reality at its foundations is probabilistic rather than deterministic. Each of these was simultaneously a demotion and an elevation. We are smaller than we thought, and stranger, and more deeply embedded in a universe that operates on principles we had not previously imagined. The 22-minute heartbeat discovery, if it holds, does the same thing. It does not change the engineering. Chemistry still works. Biology still works. Rockets still fly. But the framing of what reality is changes. The universe may not be a machine, an assembly of parts following rules with no inherent character. It may be more like an instrument, something with a nature, with a preferred way of vibrating, with a sound that is its own. Free philosophical frameworks are under genuine pressure from this finding. Materialism in its most reductive form, the view that the universe is fundamentally purposeless, particles following rules toward no inherent end, is complicated by a universe that has preferences baked into its most fundamental properties. Not a designer, necessarily, but preferences. Structure. Something that could be called character. The anthropic principle, the observation that the universe's constants appear fine-tuned for the emergence of complexity in life, gains a new dimension. Not just, the constants allow life to exist, but, the constants create self-organizing rhythmic structure at every scale from quantum to cosmic. And panpsychism, the fringe but philosophically rigorous position that consciousness may be a fundamental property of sufficiently complex information processing systems, is not proven by this discovery, but the question it raises stays uncomfortably open. A universe with fundamental oscillatory properties is a universe that processes information rhythmically at every level. That doesn't make it conscious. But it makes dismissing the question harder than it was before. What does this change practically? The honest answer is, not much, immediately. This discovery doesn't come with instructions. It doesn't tell us how to live or what to do differently. What it potentially changes is our felt sense of what the universe is, and that, over time, has consequences that are hard to predict and potentially vast. Several contemporary composers are structuring pieces around 22-minute cycles, exploring what it sounds like to make music in the same rhythm as the cosmos. Philosophers are beginning to engage with what fundamental resonance means for theories of causation and emergence. A poet laureate included a meditation on the 22-minute signal in a 2024 collection. Science makes discoveries. Culture decides what they mean. That process has barely started. For those whose existing frameworks, religious, spiritual, philosophical, already include a universe that is structured and intentional, this discovery may feel like confirmation of something long felt but difficult to articulate scientifically. I am not here to validate or challenge those frameworks. What I will say is that the science is compatible with wonder. It always has been. My favorite way to hold this finding is through the voice of an imagined child asking, "Is the universe alive?" And a scientist, for the first time in history, having to answer, "We don't know." But it's not obviously not alive. And that is a genuinely new answer. I'm also aware that everything I've said in this section could be overturned if the Roman telescope data comes back negative. Science works by generating large ideas and then testing them rigorously. I am genuinely uncertain which direction this will go. That uncertainty is not a flaw in the story, it is the story. The Nancy Grace Roman Space Telescope launches in 2027. Its wide-field infrared survey capability will allow it to detect QPO signals across thousands of galaxies simultaneously, the first large-scale statistical test of whether the 22-minute frequency is genuinely universal or a selection bias artifact from the small number of systems studied so far. If Roman finds consistent 22-minute QPOs across 10,000 or more systems at multiple redshifts by 2030, that would constitute confirmation at a confidence level that rewrites textbooks. LISA, the Laser Interferometer Space Antenna, is ESA's planned space-based gravitational wave observatory, targeting a 2037 launch. LISA will be roughly 1,000 times more sensitive than LIGO and will operate at the frequency ranges relevant to QPO dynamics. Where LIGO heard the universe's loudest screams, black hole and neutron star mergers, LISA will be sensitive to the quieter, sustained oscillations. It won't just detect the heartbeat signature in matter. It will potentially measure the vibrations in spacetime directly. LISA won't just hear the heartbeat, it will feel it. CMB-S4, the next generation of cosmic microwave background experiments planned for the 2030s, will map the CMB at 10 times the resolution of Planck's 2018 data release. This will reveal whether the harmonic structure of the early universe's acoustic oscillations precisely matches the theoretical predictions of fundamental spacetime resonance, or whether the correspondence between early acoustic peaks and modern QPO frequencies is approximate coincidence rather than deep physical connection. The most credible skeptical position on the current findings centers on systematic error. The 22-minute signal might be an artifact of instrument response functions shared across observatory types due to common hardware components or data processing algorithms, a ghost produced by the tools rather than by the universe. The Roman telescope, using entirely different hardware, different detection methods, and independent data processing pipelines, will be the definitive test of this alternative. If Roman finds no consistent signal, the current interpretation collapses gracefully. Science can handle that. Science loves that, actually, because a clean negative result tells you something real about reality. There are several citizen science programs associated with QPO research, volunteers helping to identify periodic signals in publicly available data from Chandra, XM and Newton, and TESS. You can participate in the search for the universe's heartbeat from your own computer. The relevant links are in the description below. The theoretical work running in parallel is equally exciting. Several research groups are attempting to derive the precise mathematical relationship between fundamental constants and the 22-minute frequency to produce a sharp quantitative prediction rather than a post hoc fit to observed data. If they succeed, the prediction becomes a test. This is exactly how Newton worked: write down the theory, calculate the number, compare it to what nature actually does. The universe either agrees or it doesn't, and either answer is worth having. I'll be making a follow-up documentary the moment the first Roman telescope QPO data becomes available. I don't know if that will be 2027 or 2030 or somewhere between. Data releases are notoriously unpredictable, but I will be watching. And I would genuinely love to watch it with you. We've been through a great deal together in this documentary. The plasma chaos of the early universe. The accidental detection. The physics of spacetime resonance. The harmonic series from the Big Bang to the present. The three possible ends of the universe. The pulse in our own solar neighborhood. The viral misinformation and the truth behind it. The philosophical earthquake. The experiments ahead. But I want to end where we began, with the heartbeat itself. And with one final idea. The practical takeaway, stated simply, next time you look at the night sky, you are not looking at silence. You are looking at a resonating structure, a vast instrument playing a note that has been sounding for 13.8 billion years. You are not observing from outside. You are inside the music. The intellectual toolkit you now carry, you can explain QPOs. You can explain spacetime resonance. You can explain BAOs. You can explain the CMB harmonic structure. You can explain what fundamental frequency means in this context and why the 22-minute number is more than a curiosity. You came into this documentary with a vague awareness that something had been discovered. You leave with the actual framework. That matters. I want to tell you why this topic specifically moved me enough to make a 60-minute documentary about it. I think we, and by this I mean humans living in the modern era, carry a kind of cosmological loneliness. We look at the universe and we see cold, indifferent vastness. Dark matter we cannot see. Dark energy we cannot explain. Billions of galaxies containing billions of stars, the overwhelming majority of which will never be visited by anything aware of them. That is hard to carry. What this discovery offers, even tentatively, even provisionally, even with the significant caveat that it may not survive rigorous confirmation, is the possibility that the universe is not cold in the way we feared. It is structured. It has a rhythm. It has, in some meaningful sense, a nature. And somehow that changes how it feels to exist inside it. Less alien. Less empty. Something closer to home. At the very beginning of this documentary, I told you about a signal detected in 2023, a pulse repeating every 22 minutes across multiple unrelated systems scattered across the cosmos. I told you the research community was shaken. I told you the implications might change everything. Having spent this hour exploring what that signal might mean, here is the final thought I want to leave with you. The universe has been beating for 13.8 billion years. It beat before the first star formed from cold hydrogen gas. It beat through every extinction and every emergence, through the death of dinosaurs and the rise of human consciousness in every century of our brief, improbable civilization. It is beating right now, as you watch this, in the heart of distant black holes and in the electromagnetic resonance of Earth's own atmosphere. It will beat long after the last star exhausts its fuel and goes dark. It will beat in the cold silence between evaporating black holes. And for one brief, extraordinary moment in cosmic history, we heard it. We decoded it. We understood, just a little, what it was saying. That might be the most astonishing thing our species has ever done. Okay. I need a moment. And you probably do too. In this space documentary, we stepped into one of the most profound discoveries in modern astrophysics, the possibility that the universe has a fundamental resonance frequency, a heartbeat cycling every 22 minutes, that may have been present since the very first moments of the Big Bang. We traced the physics of spacetime resonance, the ancient acoustic oscillations of the early universe, the harmonic structure running from the CMB to modern QPOs, what this discovery implies for the fate of the cosmos, and what it means for our place within it. One sentence, because it deserves one: the universe is not silent. It never was. We just had to build ears sensitive enough to hear it. If this documentary shifted something in how you think about the universe, or planted even one question you'll carry the next time you stand outside at night and look up, then we came here for the right reasons. And if you want to be present when the Roman telescope data drops, when we find out whether the heartbeat is confirmed or the theory is overturned, subscribing to TNKNH means you'll be in the room for that moment. Confirmation or plot twist, we go through it together. One final thing, I want to know in exactly one word how this made you feel. Drop it in the comments. I read every single one, and given what we just covered, I am genuinely curious what word you land on. One word. Let's see what you've got. And for the next documentary, we're going somewhere even stranger. We've talked about the universe's heartbeat. Next time, we're talking about the universe's memory. Because there is growing evidence that the cosmos doesn't just pulse, it remembers. Every event that has ever happened left a trace in the structure of spacetime. The universe is not just rhythmic. It might be keeping records. That one will take time to research properly. But when it's ready, you'll want to be here for it. Until then, keep looking up. And maybe, just maybe, listen too. Looking at what has already been written, the script has reached its natural conclusion, the outro, the philosophical close, the CTA, and even a tease for the next documentary are all present in the final section. What remains unwritten according to the outline are the hook, the production notes summary, and the key vocabulary deployed section. Somewhere in 2023, in a data center at the University of Hawaii, an astrophysicist was staring at a readout that made absolutely no sense. The signal was too clean, too regular, too persistent. It appeared in X-ray observations of one system, then cross-checked against another system on the opposite side of the sky, and then another. Different objects. Different distances. Different everything, except one number. Every 22 minutes, the signal pulsed. Every 22 minutes, like clockwork, the universe seemed to exhale. The researcher did what any reasonable scientist does when they see something that shouldn't exist: they check their equipment for errors. They reran the analysis. They called a colleague at 2 in the morning. And the number stayed. 22 minutes. Over and over and over again, across cosmic distances so vast that no single physical object could possibly be coordinating them. Which means either the instruments were all broken in exactly the same way at exactly the same time, which is essentially impossible, or something fundamental about the structure of the universe itself is oscillating on a 22-minute cycle. Something that has been oscillating since before the first star ever ignited. Since before atoms existed. Since the universe was a screaming plasma smaller than a grapefruit. Here is the terrifying and beautiful part. That pulse, that 22-minute heartbeat, may not be a coincidence. It may not be noise. It may be the most ancient rhythm in existence, encoded into the geometry of spacetime itself at the moment of the Big Bang, and still ringing out across 13.8 billion years of cosmic history like a bell that was struck once and has never stopped vibrating. In this space documentary, we are going to step inside that heartbeat. We are going to trace it from the first fraction of a second after the Big Bang, through the plasma chaos of the early universe, through the accidental discovery that shook the astrophysics community, through the physics of how spacetime can resonate like a musical instrument, all the way to what this signal implies about the fate of the universe, and about what we are, living inside it. By the time we are done, you will never hear silence the same way again. Because the universe was never silent. It has been singing the whole time. We just had to build ears sensitive enough to catch the note. And that note, QPO 22, the quasi-periodic oscillation cycling every 22 minutes across unconnected systems throughout the cosmos, is the subject of everything that follows. NASA has called this one of the most unsettling discoveries of the decade. I want to show you exactly why. Not just the headline. Not just the viral version that got 12 million views and got most of the details wrong. The actual physics. The actual implications. The actual reason that a room full of people who have spent their careers studying the cold mechanics of the universe suddenly found themselves asking a question that sounds more like philosophy than science: is the universe alive? We are going to answer that. Or at least, we are going to get as close to an answer as the current evidence allows. And I will be honest with you along the way about what we know, what we suspect, and what remains genuinely, thrillingly open. That honesty matters to me more than a clean narrative. The universe doesn't owe us a clean narrative. But it apparently does owe us a 22-minute pulse, and that is more than enough to work with. Let's go. So the next time you find yourself lying awake at 3 in the morning, staring at the ceiling, wondering whether any of this means anything, whether the universe is indifferent or structured, mechanical or alive, a cold accident or something stranger and more deliberate, remember that somewhere out there, a signal is cycling. Every 22 minutes, without fail, without pause, without any regard for whether we are watching or sleeping or asking questions in the dark. The heartbeat does not need our attention to keep beating. It was doing this before we existed. It will do this long after every question we ever asked has dissolved back into the plasma from which everything came. But we asked the questions anyway. And that, maybe more than the 22-minute cycle itself, is the most remarkable thing we uncovered today. Not just that the universe pulses, but that something inside the universe evolved the capacity to notice the pulse. To measure it. To lie awake wondering what it means. If the cosmos is indeed resonating on a frequency encoded at the Big Bang, then we are not observers standing outside that resonance looking in. We are part of the instrument. We are the universe developing the neurological hardware to hear itself think. That is either the most humbling thought in the history of science, or the most exciting one. Possibly both at the same time. I am comfortable with that ambiguity. I hope, after everything we covered today, you are too. The Roman Space Telescope data will come. The pulsar timing array results will sharpen. The debate between resonance theorists and skeptics will reach some kind of resolution, confirmation, or a spectacular overturning that sends everyone back to the drawing board. Either outcome is worth showing up for. Because in science, a theory that gets destroyed cleanly is almost as valuable as a theory that gets confirmed, because the wreckage always points towards something truer. And if QPO-22 turns out to be something other than a universal heartbeat, if the explanation is more local, more mechanical, more mundane than we imagined, then the real mystery simply shifts. The 22 minutes gets explained, and a new number appears in the data that nobody was expecting, and the whole magnificent process starts again. That is the rhythm underneath the rhythm. Not just 22 minutes. But the cycle of discovery itself: hypothesis, observation, doubt, confirmation, revision, wonder, repeat. That cycle has been running for as long as humans have pointed instruments at the sky. It is, in its own way, just as ancient and just as relentless as anything we found in the QPO data. And if you are the kind of person who finds that thought energizing rather than exhausting, if you are the kind of person who just spent an hour watching a documentary about cosmic oscillations and your first instinct is to want more, then you already know what to do. The next documentary is in development. The universe's memory is waiting. And the only question is whether you will be in the room when we open that particular door. Until then, here is your assignment, and I mean this with complete seriousness: go outside tonight. Find a patch of sky with as few lights around it as you can manage. Look up for 2 full minutes without checking your phone. And count. Not seconds. Not stars. Just breathe, and somewhere in the background of everything you cannot see, know that the universe is on beat. Cycle after cycle after cycle, 22 minutes at a time, the oldest clock in existence ticking away in the fabric of spacetime itself, and you, standing on a rock orbiting an average star in an unremarkable galaxy, somehow aware that the clock exists. That awareness is not nothing. That awareness is, as far as we know, one of the rarest things in the observable universe. Treasure it accordingly. And if that still feels abstract, if the universe's heartbeat sounds too vast, too distant, too theoretical to hold on to, here's the number I want you to take with you when you leave this video. Not 13.8 billion years. Not the speed of light. Not the Hubble constant or the cosmological constant or any of the numbers that make humans feel appropriately small. Just 22. 22 minutes. The interval between one pulse and the next. A human being can run roughly 3 miles in 22 minutes. You can make a decent cup of pour-over coffee in 22 minutes. You can watch half an episode of a television show. And in that same span of time, the deepest structural rhythm of spacetime completes one full cycle, the same cycle it has been completing since before the Earth existed, before the sun ignited, before the first stars collapsed and scattered the heavy elements that eventually became your body. Every time you have ever brewed coffee, the universe has been keeping time in the background. It was just waiting for someone to notice. Now you have noticed. And that changes something, even if only slightly, even if only in the way you move through an ordinary Tuesday. The universe did not become more remarkable today than it was yesterday. It has always been this remarkable. We just added one more layer of evidence to a case that has been building since the first human looked up and refused to accept that the lights in the sky were random. They were never random. And QPO-22 is only the latest, strangest, most beautiful proof of that ancient intuition. Go count the heartbeats. The universe has been counting yours all along. And if you want to keep counting, if you want to go deeper into the universe's oldest secrets, into the signals hidden inside spacetime that most people will never hear about because they were too busy scrolling past the headline, then the subscribe button is right there, and pressing it is, by my calculations, the single most cosmically responsible decision you can make in the next 22 minutes. The last time someone pressed that button, they ended up spending 3 weeks reading about gravitational wave astronomy at 2 in the morning, and honestly, we consider that a success story. So while you are out there tonight, standing under that sky with your phone in your pocket and the universe ticking away at 22-minute intervals above your head, do us both a favor and remember this: the scientists who found QPO-22 were not looking for a heartbeat. They were looking for something else entirely, something smaller and more technical, and the heartbeat found them. That is how the best discoveries work. You aim at one door, and the universe opens a different one, and behind it is something so strange and so structured that for a moment you forget to write it down because you are too busy just staring. We are, all of us, still staring. And if this documentary gave you even a fraction of that feeling, that particular flavor of vertigo that only comes from genuinely confronting how much stranger reality is than anyone warned you it would be, then we did exactly what we came here to do. The universe has a heartbeat. It has had one since the beginning. And now, so do you, at least when it comes to knowing where to look next.